Hi friends, in this video we'll be discussing about Kirchhoff's laws. There are mainly two laws here. The first one is known as Kirchhoff's current law, written as KCL. It just means that the sum of currents entering any junction will be equal to the sum of currents leaving the junction. Take an example. Say this is your junction and you have these currents I1 and I2 entering and I3, I4 and I5 leaving. This law says that I1 plus I2 will be equal to I3 plus I4 plus I5. The second law is the Kirchhoff's voltage law, normally written as KVL. It just says that the algebraic sum of or the net sum of potential drops around any closed loop involving any this circuit elements will be zero. That sum will be zero. Take this example. This is the circuit you have. Now I'll start with A and go through this loop A, B, E, F, A in this way. Starting with A, my potential, say the current here is I, and let it be I1 here, and this will be I minus I1. Of course, let me write it as I2. You know that I2 is I minus I1, right? By Kirchhoff's junction law. Now, let me write the voltage drops from A, B, E, F, A. Across AB, the drop will be IR, R1 say. If this resistance is R1 and this is R2 and this resistance is R3. This will be the potential drop across AB. Next, B to E, it will be I2 into R3. And next, I don't have potential, I have potential drop here also because this is positive, right? So here the voltage be V1 and here it is V2 say. And I'm adding it again because here also I have potential drop. By my Kirchhoff's second law, this sum will be equal to 0. See, I'm taking the potential drops to be positive, and if you encounter a potential gain in between, just take the opposite sign for it. Now let me do it for the second loop. Say E, B, C, D, E. For this loop E, B, C, D, E, I'll start from E. The potential drop will be minus I2 R3. What does this mean? Because I'm going opposite to the direction of current from E to B. So it's not potential drop, it is potential gain actually. So I wrote it with a negative sign. Next, I'll have a potential drop of I1 R2 from B to C. And next I have a gain of V2. So I'm writing it with a negative sign. That's it. You'll end up with E again. This will be equal to 0. Observe this. I'm taking the potential drops to be positive and potential gains to be negative. Some people do it the other way. However, it doesn't matter because finally you are equating it with a 0, right? Doing it the other way just means that you are multiplying the equation with a negative sign. If you have some other complex circuits, like you have some resistance over here and some other like this, something else. If you have some other circuits like this, the method is the same. Take the similar equations for all the loops, write similar equations for all the loops, and you'll get some big equations, many equations. And obviously, you will be knowing some of the variables, and you will have to find the others, and just solve all the equations. You will get the result. And there is one more thing I need to say you. If after solving all these equations, if you got the current value, say to be some negative minus 3 amperes, what does this mean? It just means that the direction you assumed for this current I1 is wrong. The magnitude is the same, but the negative sign indicates that your I1 is in the opposite direction of the direction you have assumed it. That's it. This is the proper method to solve any circuit. Now we'll go for a problem through which you can appreciate Kirchhoff's rules even better. This is the problem. The cube you see, take every edge to be a resistor. Say and say this is a resistor, this is a resistor. Assume all of these have some equal resistance R. This one has R, this one, all the 12 edges. And the problem is I have to find the equivalent resistance of this system. Now, hope the question is clear till now. Of course, across what? Say this is one end which is connected to some potential difference, and this is the other end across the body diagonal. Now I want to calculate the effective resistance of this cube across the points AB. Okay, or I'll name them in a different way, across the point OP. So hope the problem is clear. I'll name each of these corners also. Let this corner be A, B, C, D, and let these corners be A dash, B dash, C dash, and D dash. Now, say there is some current here. I'm taking it to be 3I. Of course, I don't know I, so it doesn't matter. And you may take as well the current to be I. There are many methods to solve this one, but what I am discussing is one of the smart ones. Now, to solve this, we need to take something called as symmetry into consideration. Check this. You know that 3I current enters from this wire. Okay. Now, what is its future? Observe this. The resistor between A dash is no greater than the resistor between A and D. Are you getting me? And similarly, the resistor between A and D is no greater than the resistor between A and B. All the three, this resistor, this one, and this one, are in equal electrical environment. Did you get this point? I'm trying to use the symmetry in this circuit. So, by symmetry, if my current is 3I here, which enters, since all these three resistors are something like brothers, so they should get some equal distribution, right? So I'll finally say that the current through this wire A dash is I, and similarly you have I current through AD also, and similarly you have I current here also. Hope this is clear now. I'm just trying to use the element of symmetry here. And now take care of this. You have this I current going from here to here, okay? And now it has to divide, okay? You have AD dash here, A dash B here, two resistors of equal resistance. So again, by symmetry, I can say that I by 2 current goes through A dash D dash, and I by 2 current goes through A dash B dash, because they two are same resistors. Those two resistors are having same resistance, and they are in equal electrical environment. So by symmetry, here the current division is I by 2, I by 2. By using the same principle, here the current I, which flows from A to B, also gets divided into I by 2 and I by 2 here. And the similar thing takes place here also. Here. Observe this. And the I by 2 current coming from A dash B dash and B to B dash gets added up here, and you get a current I here again, which is going from B dash to C dash. Okay. Similar thing happens here also, because this is obvious, because D dash C dash, B dash C dash, and C C dash, even those three resistors are equal and they are in equal electrical environment. So by symmetry, even they should carry the same currents, right? So these principles are very handy actually. You can use symmetry to find many other variables also, like I can also say that the potentials of A dash, D and B are same just by symmetry. Verify it if you want. We'll take the help of Kirchhoff's voltage law to solve this question. Now check this. I want a loop, right? I'll start from here, go this way, and here I'll go from A to A dash, then A dash to B, B dash to C, and then come back. So this is my loop, okay? I'll write voltage drops for all the resistors and batteries here in this loop, okay? Starting from this point, I'll go like this. First, I encounter a potential drop across A to A dash. That will be IR by Ohm's law. And next from A dash to B, there will be a potential drop of I by 2 is the current and the resistance is R. And next from B dash to C dash, there is a potential drop of I and R. And finally, I get a potential gain of this battery when I come like this. So I'll minus this. This is your first equation, okay? Please forgive me. The only reason I'm not taking a new slide is I feel that you like to keep on seeing this diagram for better understanding. That's why I'm writing it here, even though it is a bit clumsy. Okay, however, now check this. This is your equation, right? IR plus I by 2R plus IR minus V. I can write the same equation as V is equal to what is IR plus I by 2R plus plus IR again. It is what? 5 by 2, right? It is 5 by 2R. Okay. Now V is equal to 5 by 2 IR. Okay. This is my final equation, or the same equation written in some other form. What can we infer from this? V is your net voltage. So if I replace a single resistor of equivalent resistance across O and P, that is A and C dash, I should get a equation something similar to this, right? Now let me take a new slide at least. See, V is equal to 5 by 2 IR. This is your equation. And if I replace the entire system with a single resistor which has some equivalent resistance Req, say, then my current which enters from the battery is 3I. Note this. You are what? Prone to make a mistake here. It's not I. I took the current to be 3I at the beginning. So this current into the resistance, this should give me the potential difference across those two endpoints of the diagonal, of the body diagonal, right? And you have this equation here. You have this equation here. What can we observe from these two? Equate them and you will get something like Req into 3I is equal to 5 by 2 IR, right? I gets cancelled. So Req is what? 5 by 6R. We solve the problem. It's over. So the net effective resistance across those two body diagonals is 5 by 6R. Now what I'll do is I'll just take some other path just so that I want you to appreciate the Kirchhoff's second law. That's why I'll start from B again. From this point I'll go like this. Next, instead of going from A to A dash, I'll take a turn. I'll go from A to B, then I'll go from B to B dash, then I'll go from B dash to A, then from A dash to D dash, then from D dash to P, and then again the same way. Now this is a bigger loop, right? So what I'll do the same thing. I'll write the potential drops across all those elements or resistors for this big loop using the same Kirchhoff's second law. I am really very sorry, there is no place here. From A to B, there is a potential drop of IR. Then from B to B dash, there is a potential drop of I by 2 into R. Then from B dash to A dash, observe this, there is no potential drop, but there is potential gain because we are traveling in a direction opposite to the direction of current. Observe this. Current is from A dash to B dash and we are going from B dash to A. So I'll write minus here. And magnitude is I by 2 into R. Then from A dash to D dash, it is plus I by 2 R. And from D dash to my final point C dash, it is IR again. And it is a potential drop. Sorry. And finally, I'll encounter a battery, which is a potential gain. So, what you got here? You got a similar equation actually. I mean the same equation. V is equal to 5 by 2 IR. What does this mean? You're going to get the same result again, Req. So it doesn't matter what loop or what path you choose. Finally, you're going to get the same answer, or I mean to say that Kirchhoff's loop law. It works for any loop in a circuit. Hope you enjoyed this video. That's it for today. Keep watching. Bye.